Skyscrapers rise hundreds of feet into the clouds, but before they could reach the sky, workers had to conquer the treacherous world beneath our cities. No excavators, no machines, just teams of men with picks, shovels, and layers of mud, threatening to swallow every effort. Manhattan and Chicago builders faced soil so unstable that shallow footings would simply fail. So how did they dig foundations deeper than a 10-story building? By hand. The answer exposes a forgotten battle with nature itself and reveals why every step upward started with a staggering fight downward. Mud, clay, and waterlogged soil defined the hidden world beneath Manhattan and Chicago. Builders faced a puzzle that had no easy answer: how to support a mountain of steel and stone on ground that shifted with every rainfall. In lower Manhattan, the earth was layered like a cake, thin crusts of fill and sand, then thick beds of soft clay, all floating above bedrock that sometimes lay more than 100 feet down. When workers tried to anchor buildings on shallow footings, the ground simply gave way. Walls cracked, floors tilted, and entire structures threatened to sink. Chicago brought its own challenges. The city was built on a former swamp, its surface a patchwork of silt and peat resting atop a deep clay basin. Here, the bedrock was too far to reach with early tools, so builders had to contend with soil that squished and settled under even moderate weight. The risk was not just inconvenience, it was collapse. Heavy masonry walls needed a stable base, but the upper soil had little strength. The Monadnock building in Chicago, finished in 1891, stretched these old methods to the limit. Its brick walls were so thick at the base they left little room for anything else on the ground floor, and even then engineers worried the building might buckle or shift. In both cities, water seeped into every pit. Dig too deep, and the hole filled as fast as it was emptied. Frost heaved the ground in winter, while summer rains turned excavations into muddy traps. Every layer down brought a new obstacle: saturated sand that flowed like liquid, sticky blue clay that clung to boots and shovels. And below it all, a promise of solid bedrock that often felt impossibly out of reach. The soil profiles dictated the rules. In Manhattan, the hope was always to reach bedrock, but the cost and danger grew with every foot. In Chicago, the answer was not so simple. Sometimes there was no practical way to reach the stone below. Builders needed new strategies, but before any innovation could take hold, they first had to confront the stubborn reality of the ground beneath their feet. Men lined up at the edge of the pit, boots caked in mud, hands wrapped tight around wooden handles. The work began before sunrise and ended only when daylight faded. Picks broke the first crust, shovels followed, and every load of earth had a destination: a waiting bucket, a wheelbarrow, or a battered cart. Crews worked in relay, each team spelling the next, the rhythm as steady as breath. In the shallow days, a single line of men could clear a trench, but as holes deepened, the numbers swelled, dozens and sometimes hundreds, all moving in a tightly choreographed dance. Buckets rose and fell by hand, each one carrying just a fraction of what modern machines could lift in a single scoop. As the pit grew, so did the challenge. Every extra foot meant more time hauling earth up, more men needed on the ropes, more sweat lost to the air. Chains of laborers passed buckets hand to hand, up makeshift ladders or along rickety planks. Above, another crew steered wheelbarrows to the street, dumping loads onto growing mounds of spoil. A good team could remove a few cubic yards in a day. But progress slowed as the hole went deeper. The walls pressed in, the air thickened, and water seeped up from below. At 50 feet down, it took a full shift just to clear what had collapsed overnight. The tools were simple: pick, shovel, steel bucket. There were no shortcuts. When the ground was soft, it caved in behind them. When it was clay, it clung to boots and blades, each shovelful a small victory. Yet there was a limit to how many men could fit at the bottom. a limit to how far muscle and grit could go. The deeper they dug, the clearer the ceiling became, not in stone, but in human endurance. Every bucket lifted by hand was a reminder. This was a battle against the earth itself, and the earth was winning. The need for a better way pressed in from all sides, setting the stage for a new kind of foundation, one that would change the rules of building forever. A caisson, in its simplest form, is a giant box built to sink. In the 1860s and the 1870s, engineers crafted these chambers from thick oak beams, iron plates, and waterproof coatings, assembling them right at the edge of rivers or city streets. Some caissons stretched over 80 feet long and 60 feet wide, like the ones used for the Eads Bridge in St. Louis. The walls rose high above the ground, but it was the bottom, the working chamber, that mattered most. This space, sometimes only 9 feet tall, was sealed tight, reinforced to withstand the crushing weight of mud and water above. The process began with the caisson resting on the surface, open at the bottom and closed at the top. Crews lowered it into a freshly dug pit, then climbed inside to start digging. As they removed soil from beneath the box, the whole structure settled deeper under its own weight, inch by inch, day by day. The oak and iron frame pressed into the earth, guided by gravity and the careful hands of the men below. When the caisson met resistance, roots, boulders, or dense clay, workers hacked away with shovels and picks, never far from the threat of collapse. In St. Louis, the Eastern Pier caisson for the Eads Bridge began its descent in October 1869. Over 3 weeks, laborers inside the chamber chipped away at the riverbed, while above them the structure slowly vanished from sight. By February 1870, the caisson had reached bedrock, more than 100 feet below the surface. The walls, built from layers of timber and iron, held back the river and the shifting mud. Inside, the air was thick and dim, but it was dry, a small miracle in a world where water seeped through every crack. This was the breakthrough. The caisson created a dry, stable chamber where men could work far below the waterline. Once the digging was done and the bottom reached solid rock, the chamber was filled with concrete, locking the foundation in place for good. The method worked because the box sank as it was emptied, always moving downward, always pushing aside the earth that tried to swallow it. The deeper the caisson went, the more pressure built up around it, forcing engineers to invent new ways to keep water out and air in. Even before the age of compressed air, the sinking caisson was a feat of patience, calculation, and brute force, a box that carried men and tools into the depths, 1 foot at a time. Air was the invisible shield standing between the workers and disaster. In the depths of a caisson, every inch below ground brought more water and mud pressing in, threatening to flood the chamber. Engineers fought back with compressed air, pumping it into the sealed workspace to hold the earth and water at bay. The principle was simple but unforgiving. The air inside had to push outward just as hard as the water and soil pushed in. If the balance tipped, even for a moment, the chamber could flood in seconds. Maintaining this pressure required a constant, carefully measured airflow. Steam-powered compressors above ground forced air through thick iron pipes into the caisson below. The pressure inside the working chamber often reached 2 or 3 times that of the surface, enough to keep the river or groundwater out, but not so much that the structure or the men inside would be at risk. Any sudden drop in pressure could spell disaster. The air had to be kept moving, fresh enough to breathe and steady enough to keep the chamber dry. Above ground, engineers watched pressure gauges as closely as a ship's captain tracks the horizon. Getting in and out of this pressurized world was a procedure all its own. Workers entered through airlocks, small double-doored chambers built into the caisson wall. The process was methodical. A man would step into the airlock, closing the outer door behind him. With a hiss, the pressure inside the airlock would be increased to match that of the main workspace. Only then could the inner door be opened, allowing safe passage. Leaving was the reverse. Close the inner door, slowly reduce the pressure, and only then open the outer door to the world above. Rushing this process could have deadly consequences. Each airlock cycle was carefully timed. The pressure had to equalize slowly, not just to protect the caisson, but to protect the men themselves. Too fast, and the sudden change could cause severe pain, paralysis, or worse. This problem would soon become infamous as caisson disease. For now, though, the routine was everything. Every shift, workers followed the same steps: enter the airlock, wait for the pressure to build, pass through the inner door, and descend into the dim, pressurized chamber. Inside, the air felt thick and heavy, and the sound of compressors never stopped. But the water stayed out, and the work could continue, one shovelful at a time. The entire operation depended on the invisible balance of pressure and routine. Without this constant, carefully managed airflow, the caisson would have been just another box lost to the mud. Instead, it became a safe haven, at least for a few hours at a time, where men could dig toward bedrock, protected by nothing more than air held under pressure. Inside a pressurized caisson, every breath carried a hidden danger. When men worked under compressed air, nitrogen from the atmosphere dissolved into their blood and tissues. As long as the pressure stayed high, the gas remained harmless. The real threat came at the end of a shift. If a worker left the caisson too quickly, rising from 2 or 3 atmospheres back to the surface in minutes, the sudden drop in pressure forced nitrogen out of solution. Tiny bubbles formed throughout the body, blocking blood vessels and damaging nerves. The result was a condition known as caisson disease, more commonly called the bends. Joint pain was the most common complaint, described as a deep, twisting ache that left men doubled over. In severe cases, bubbles traveled to the spinal cord or brain, causing paralysis or even death. Some workers collapsed on the spot, unable to move or speak. Others felt a creeping numbness in their limbs or lost control of their muscles hours after leaving the chamber. In the worst outbreaks, dozens of men were left crippled, and fatalities climbed with every new project. Doctors in the 19th century struggled to make sense of the illness. Early theories blamed bad air, overexertion, or simple exhaustion, but the true cause remained elusive. Medical officers like Dr. Andrew Smith on the Brooklyn Bridge counted more than 100 cases among caisson workers, but had no cure to offer. Rest, warmth, and strong tea were the only treatments. It was not until 1878 that French physiologist Paul Bert proved nitrogen bubbles were to blame. Even then, most sites lacked the equipment for staged decompression or recompression therapy. The bends became an accepted risk, a price paid for progress underground. For every foundation dug with compressed air, there was a silent tally. Men struck down by pain, left with twisted limbs, or lost entirely to a disease no one yet understood. Each descent into the caisson was a gamble, with the odds growing worse the deeper the work went. The invisible threat inside those chambers shaped every shift, casting a long shadow over the promise of building upward. Washington Roebling stepped into the Brooklyn Bridge caisson in the winter of 1872, determined to drive progress deeper than anyone thought possible. The air inside was thick, the pressure immense, and the work unrelenting. He stayed longer than any other supervisor, sometimes 12 hours at a stretch, pushing through pain to keep the project moving. But the cost was immediate and personal. One morning, after a long shift below the East River, Roebling collapsed. He lost feeling in his legs, struggled to speak, and found his vision dimming. In his own words, he described a peculiar numb feeling in the small of the back and lower limbs, which precedes paralysis. The diagnosis was caisson disease, the bends, a condition barely understood at the time. He never fully recovered. For the rest of the construction, Washington directed the work from his sick room, watching the site through a telescope and writing instructions in shaky script. The bridge could have stalled then and there. Instead, Emily Warren Roebling stepped forward. With no formal engineering training, she learned the technical details on the fly, reading Washington's notes and consulting his books. Every day she crossed the construction site, relaying messages, overseeing crews, and answering questions from skeptical officials. She managed the flow of materials, checked calculations, and even negotiated with city leaders to keep her husband's position secure when others tried to push him aside. Letters from the period show her handwriting on orders and technical explanations, her presence woven into every major decision. The Roeblings' partnership became the backbone of the project. Washington's mind guided the bridge, but Emily's hands and voice carried out his will. Their story is a reminder that the risks of foundation work were never just technical, they were deeply human. The dangers inside the caisson did not end with the men who dug the mud. They reached into homes and families, shaping the lives of everyone connected to the job. The Brooklyn Bridge would stand as a marvel of engineering, but also as a testament to the resilience and sacrifice of those who refused to let tragedy halt progress. Steam engines changed the rhythm of the foundation site. Where muscle alone had once set the pace, now the hiss and clatter of boilers filled the air. Above the pits, derricks swung on iron pivots, their arms reaching deep into the earth. Each was powered by a steam hoist, a machine capable of lifting several tons at a time. Buckets loaded with clay, sand, and broken stone rose steadily, chained together in a loop that never seemed to stop. Some of the largest hoists, like those seen on the Brooklyn Bridge and later Skyscraper sites, could pull up over 1,000 cubic feet of earth in a single shift, far more than any team of men could manage by hand. The steam hoists did not replace the laborers below, but they multiplied their reach. As men dug deeper, the buckets grew heavier, and the climb to the surface stretched longer. A single misstep could mean a load swinging out of control or a cable snapping under strain. Foremen watched the gears and pulleys closely, their eyes trained on every moving part. Above the chaos, the steady thump of pistons set the tempo for the day's work. Foundation stones, some weighing several tons, arrived on site by rail or barge. Steam derricks lifted these blocks from the street and lowered them with slow precision into the waiting pits. The stones had to be placed just right, each one forming part of the base that would carry the weight of a skyscraper. Crews used block and tackle rigs, shouting signals through the noise, guiding each stone into position with crowbars and ropes. The process demanded patience and teamwork. A stone set just 1 inch off could throw the entire foundation out of line. When the digging reached bedrock, another team took over. Powder monkeys, young men skilled with explosives, moved in with hand drills and sticks of dynamite. They worked by lantern light, drilling holes into the stone, packing them with powder, and running fuses to a safe distance. Timing was everything. Blasts were scheduled during lunch breaks, when most of the crew was above ground. The ground would shake, dust would billow up the shaft, and then, after the all clear, the powder monkeys returned to clear away the shattered stone. Each blast brought the foundation a little closer to its final depth. By day, the site ran like a machine, steam hoists hauling, derricks spinning, buckets rising and falling in a steady flow. Every shift depended on the seamless handoff between men and machine, sweat and steam. The work never truly stopped. As dusk approached, the focus would shift to keeping water out and holding the ground firm. But during daylight, the foundation pit was a hive of motion, powered by fire, iron, and the relentless drive to build higher. At the edge of the river, the real enemy wasn't just mud or clay, it was water, always threatening to reclaim the ground. Crews answered with cofferdams, building thick walls of timber or iron sheet piles driven deep into the riverbed. These barriers formed a box around the future foundation, forcing the river to flow around instead of through. Once the walls were in place, pumps worked day and night, drawing out thousands of gallons every hour. Even a short lapse meant water could surge back in, undoing days of effort in minutes. Night brought its own set of hazards. As daylight faded, the job didn't stop. Crews lit the site with limelight, blocks of quicklime heated by jets of oxygen and hydrogen, casting a harsh, ghostly glow across the mud and water. The white light cut through the mist, turning the riverbank into an eerie stage where every movement was visible, every mistake exposed. Night teams took over, their task clear and relentless. Keep the pumps running, patch leaks in the cofferdam, and watch the water line for any sign of rising tide or shifting current. The pumps themselves were a lifeline. Some sites ran 2 or 3 in tandem, each capable of moving hundreds of gallons per minute. If a hose clogged or a valve failed, alarms were shouted up and down the line. Men scrambled to clear blockages with hammers and iron rods, racing against the slow but steady creep of water. On stormy nights, the river pressed harder, testing every seam and joint. A single breach could send a torrent rushing in, turning the excavation into a churning pit in seconds. Coordination was everything. Crews worked in shifts, handing off responsibilities with quick words and hand signals. Foremen counted heads and checked pump gauges, knowing that fatigue could dull senses and slow reaction times. The constant roar of water and machinery filled the air, making shouted warnings hard to hear. In the darkness, even a small misstep, a missed signal, a forgotten valve, could have consequences for everyone below. Through it all, the river never gave up. The struggle to keep water out was a contest measured not in days, but in hours, sometimes in minutes. The cofferdam and its pumps stood as the only line of defense, holding back a force that never truly slept. For the crews working under limelight, every shift was a reminder that nature was always waiting for a chance to break through. A single sound could decide the fate of everyone underground. In the foundation pits and caisson shafts, noise ruled every moment, steam hoists thumping, pumps rattling, men shouting over the grind of machinery. Yet buried in this chaos, the only way to coordinate was often a length of wire and a bell. Foremen and signalmen depended on these bell-pull systems to send commands between the surface and crews far below, where voices vanished in the distance, and the air itself seemed to muffle every word. One ring might mean raise the bucket, 2 might mean lower it, 3 could be an emergency. But when the shaft stretched 100 feet and the air was thick with steam and dust, even a simple signal could become a riddle. Mistakes happened. A missed pull or a bell muffled by the echo of a nearby hoist could send a bucket crashing down before the men below had cleared the way. In some cases, workers found themselves trapped as a load of stone descended, unable to scramble out in time. There were stories passed from crew to crew of men buried by falling spoil, or of a caisson chamber suddenly flooding when a pump was shut off at the wrong moment. In the worst cases, a single misunderstood bell meant air pressure dropped without warning, sending water and mud surging into the workspace and forcing a frantic escape through the airlock. The risk was constant. Foremen watched the ropes and listened for the faintest sound, knowing that one wrong signal could turn routine into disaster. Signalmen, perched at the shaft's edge, strained to hear through the din, their hands sweating on the bell cord. The deeper the dig, the greater the lag. Sometimes several seconds passed before a pull above reached the bell below, and in those moments, a crew's fate might hang in the balance. Fatigue blurred the senses, especially on night shifts when calcium limelight cast harsh shadows and exhaustion dulled reaction times. In the confusion, a bell could be missed, or answered twice, or mistaken for a different command entirely. When the work was at its most intense during a heavy lift, or as water threatened to break through, every man relied on the system holding together. There was no backup. Even as steam engines and new machines took over more of the heavy lifting, the fragile chain of human communication remained. It was a system built on trust, repetition, and the hope that in the next moment, the bell would ring true. For the men below, every signal carried the weight of life and death, and the knowledge that a single error could bring the whole operation to a halt. By the end of the 19th century, the sound of steam shovels began to echo across construction sites in New York and Chicago. These hulking machines, powered by roaring boilers and driven by teams of engineers, could move earth at a pace that would have seemed impossible only a decade before. Where armies of men had once labored for weeks to clear a foundation pit, a single steam shovel could carve away the same volume in a matter of hours. The first machines appeared on the largest projects, railroad cuts, canal works, and soon enough, the foundations of the city's tallest buildings. Their jaws bit into clay and sand, lifting cubic yards of soil with each swing, dumping it into waiting carts or onto conveyor belts that whisked spoil away from the site. The arrival of mechanization did not erase the need for human skill. Steam shovels required careful handling. Operators worked levers and gears with practiced hands, judging the angle of each cut and the weight of every load. Laborers still worked alongside the machines, guiding their progress, clearing jams, and managing the endless flow of material. But the balance had shifted. What once demanded hundreds of hands now depended on a handful of skilled operators and the relentless power of steam. Hydraulic excavators introduced in the 20th century would later push this transformation even further. These new machines running on oil and steel could dig deeper and faster than anything that came before. A task that once took a crew of men weeks, digging a pit 100 feet down through water and clay, could now be finished in a single afternoon. Timelines shrank, costs fell, the city's skyline began to rise with unprecedented speed. Yet for all the progress, the foundations laid by hand and steam remain. Many of the skyscrapers that define Manhattan and Chicago today still rest on stone and concrete, placed by men whose names are lost to history. Their work, measured in sweat and patience, endures beneath the rush of modern life. Walk through the financial district or along the Chicago River, and the buildings overhead stand as proof. Each one is anchored by foundations dug before the age of modern machines, testament to what human endurance and early mechanization could achieve long before the world was remade by the power of hydraulics. Today, entire city blocks vanish beneath hydraulic arms in hours, yet the silent endurance of hand-dug foundations still holds up icons of our skylines. As climate risks and urban density push engineers deeper, the lessons of calculation, risk, and collaboration remain urgent. Every modern innovation stands atop the sweat and sacrifice of those who dug blind. The next time you look up, remember, the greatest leaps begin far below the surface. Share your thoughts below.